Hello there, and welcome to this series, Introduction to Google Colab for Research. And today we're going to talk about Tensorflow Keras. We will use a simple audio recognition example, similar to what we already did using PyTorch, using recognizing keywords, but a little bit different this time. And we are going to use Tensorflow instead of PyTorch. So here I am at tensorflow.org/tutorials/audio, simple audio, and here we have this simple audio recognition, recognizing keywords, and in this tutorial we will build a basic speech recognition networks that will recognize 10 different words. So this is just an example. So if you want to build a real speech and audio recognition system, you need much more complexity than what we're going to discuss here. But this will give you the basic foundations on how to start with doing some audio recognition using deep learning techniques and using TensorFlow. Have in mind that this is not a TensorFlow tutorial. So we have audio tutorials in our YouTube channel where we go in depth into such concepts, but here we are focusing on how to use Google Colab to research, and we can do deep learning research and use TensorFlow. So I'll of course go through some code and explain some basic concepts, but I will not go in depth in how to use TensorFlow and all the deep learning concepts that we are going to encounter in this journey. And here, of course, this is a Google Colab tutorial, and we have the possibility to run this in Google Colab. So if you click here, we will start opening here in Google Colab, loading this notebook. And now let's already configure our runtime. So we want to use GPU already configured, and let's connect, and then we can start going through the tutorial. So this is a tutorial. I didn't prepare this tutorial. This is a tutorial prepared by people from TensorFlow. So you go to their official homepage, tensorflow.org, and there you find different tutorials on different fields. You'll find documentation, and we are going to explore this specific tutorial on simple audio recognition. And we are going also to compare with the previous tutorial we have that's using PyTorch with the same principles, and probably is the same data set used. We are going to look later on in this. So here, if we click run in Colab, to open here, we will have our tutorial. This model will try to classify a 1-second audio clip as down, go, left, no, right, stop, up, and yes. So we already noticed that it's a bit more simple than the previous tutorial. And I think I believe we had more command words or more keywords. So as usual, we will start importing the necessary modules and dependencies. And this is the first time where we will see that we're going to use TensorFlow and Keras. So Keras is an API designed for deep learning, and they try to make it easier and more simple to humans, to scientists, and to people without programming expertise. Of course, you need programming, but the way they try to build the API to make life easier. Of course, we have some drawbacks. When life is too easy, we also cannot do with too much complexity, and sometimes we find ourselves not having easy access to the inner self of the libraries, and we cannot change too many things, or there's too many assumptions, too many things already predefined for you, and then if you don't have a good understanding of what you're doing, you may achieve some results, but you don't know why, and then you try to reproduce using a different library and you not be able. But we'll not go into the detail, just to know that Keras, it used to be an interface that supported multiple backends. So you could use Theano, that was a popular backend some years ago, and also TensorFlow, but now it only supports TensorFlow. So we will see that we're importing from TensorFlow Keras, we're importing layers, we're importing models, and of course we are talking about Keras, we are talking about TensorFlow. Just see, let's see some information here. TensorFlow. So here at tensorflow.org, you see this is a open source library to help you to develop and train machine learning models. And here you will find learn, and then you have introduction. So you can use TensorFlow with JavaScript. You will also have models and data sets. Here the TensorFlow documentation, how to install. So all you'll find at tensorflow.org. So we will also use Seaborn for interesting visualizations, NumPy, PyPlot, and Matplotlib PyPlot to display some results. And I will also introduce some topics that are not covered in this tutorial, but we will also use Scikit-learn, that it's another library very useful in the machine learning world. And I will create, let's split our data set for the training, validation, and testing set using Scikit-learn, Stratified Shuffle. So in this tutorial, they're using a much basic way on how to split the data set in these three subsets, but we will introduce here a bit of Scikit-learn, so you can also use Scikit-learn together with TensorFlow, together with Google Colab in your experiments. And I will also introduce a Tensorboard, how to use Tensorboard inside a Google Colab notebook and together with TensorFlow, so we can have a nice visualization of our metrics of our models. We can also visualize the layers of our models, how the structure and the architecture. So we are going to include this in this tutorial. So there will be a little difference that I will introduce in this journey. So here is a very important part, and is setting seed for experiment reproducibility. So this means that it makes possible to reproduce the results. There are a lot of usage of random numbers in machine learning, especially also to initialize values. We're dealing with distributions, we're dealing with values that are randomly initialized, of course with some constraints, but there is a lot of and the initialization in almost all optimization tools, they are very important. If you have good initialization, you can converge to a result faster. If you have very bad initialization, perhaps it's possible to convert, but we will never converge, or you'll take too long. And here, this is what we are doing. We are setting a seed. Then we have a seed for NumPy and a seed for TensorFlow. And then if the person uses the same seed, we expect to have the same results. The problem is that it's not always possible to achieve the same results, especially if we are using, for example, multiple threads, multiple cores, multiple processors, parallel processing, GPUs and different GPUs and different CPUs. So you might still, even using seed, you might still run into some problems with reproducing your results, even setting this seed. But of course, this will help you, and depending on the complexity of your problem and your experiment, you will be able to reproduce the experiment. So let's go and run the cell. So we will import our modules and dependencies. And now here there will be this part where we'll download a portion of the speech commands dataset. So it's already saying that the original dataset consists of over 100,000 WAV files. People saying 30 different words, but we will just use a small fraction of this dataset. So that is what they are calling here the mini speech commands. So they have this link here, storagegoogleapis.com, download tensorflow.org, mini speech commands. In the speech commands here, we have homepage. It's an audio dataset of spoken words designed to help train and evaluate keyword spotting systems. And here you have this description of this dataset, the PDF. Speech commands, a dataset for limited vocabulary speech recognition. So if you're interested to understand the full dataset, and of course I encourage you to later on to try to tweak this model, this tutorial, what we're doing, and include more files and use perhaps the full range of available files, so you can read the paper how they describe this data set. Now we are defining here a directory for our data. Here we already find a way, so some utility to get a file. So it downloads a file from a URL, if not already in the cache. So we have get file, then we have the file name, we have the origin, then we will have other arguments that they are all described here. So untar, it's deprecated now, and we can use extract instead of untar, and we're setting extract to true. So true tries extracting the file as an archive. For example, it can be a tar or it can be zip. And we set the cache directory to dot and the cache subdirectory to data. So the cache directory is the location to store cached files, and when none is used, it will default to the default directory, to be this one here. So this way we are going to download this mini speech command zip and already extract. So if we will look here, we have already some sample data, but now let's run the cell. It's downloading the data. So when we open here again, we see now we have a directory called data. We have here the mini speech commands zip file that we downloaded, and then we have the extracted file. So we have subfolders. Inside subfolders we would have our different files. Now the tutorial tells us to check some basic statistics about data set. Actually, it will print which commands we have in this data set. So it's go, yes, left, down, no, stop, up, and right. So we'll have WAV files of people saying these commands. Now here it will extract the audio files into a list and shuffle this list. So this tutorial is preparing to split the data set into training, validation, and test sets. The next step, so first it is extracting the audio files into a list, and then it's shuffling this list. So we would have a random distribution of the files. This is in a way so we could have all files, all types of files present in the test set, in the validation set, in the training set. And if we just split like they will try to do in the next step, it's a very simple way how to split. But if it's not already randomized, we could end up with just files go in the training set and they are not present in the validation or test set. So this is not a very good strategy. So here they are using tf random shuffle file names, this tf.io gfile.glob. So we have this data directory was set here, and they are using this IO gfile.glob into this. So it returns a list of files that match a given pattern. And they put here the string data dir, and they use these wildcards here. So there's a term, the star matches any sequence non/characters, and you can take a look on how to use this. This is what they are doing, and then they will print the number of total files. Then they will print the number of examples per label, and they will print an example of how it looks, this file tensor. So it takes file 0 from the file names, printing. So let's execute this. It takes a while. So we have a total of 8,000 files, and we have 1,000 examples per label. And we have TensorFlow tensor. There is this with this wave, and for example, this is the name of the file name. So here it will split these files into the training, validation, and test set using 8-10-10 ratio. So 80% to the training, 10% to the validation, and 10% to the test. So the way that they are doing is that now they have this list of tensors in file names, and then they will just split the files from 0 to 6,399 will be the train, then 800 more to the validation, and the last 800 to the test. Then there will be this training set size, and it will display the size of the training, validation, and test set size. So this is a way how to do it. This way, we notice that they're just shuffling, randomly shuffling this list, the first step, and then they are picking some number of files for each training set. But now we are going to use Scikit-learn, and we will introduce you to the concept of stratified shuffle. But before we move into the Scikit-learn, let's continue running a bit this tutorial, because there will be some functions that we need, some steps that we need before we use Scikit-learn. One very important thing to note now is that we have here the type. So we have a list of tensors, and this tensor type is a string, and we still need to get the label and the WAV file, the audio information from this WAV file. So we just have the name of a file at the moment. So later on we need a function that will load this WAV file, and we will have the audio data from this file, and we also need the label of this file, and the label will be, for example, the name of the command. So if it's stop, if it's no, we still don't have this. When we move on, we will see that there is a function tf.audio_decode_wave, which returns the wave encoded audio as a tensor and sample rate. And here we're defining a function, decode audio, that will call this audio decode, and then there will be a tensor returning a tensor with this audio information. And here we have a function to get the label. So we pass it a file path, it will split the string and get the label. And then it's defining a method that will take a file name of the WAV file and output a tuple containing the audio data and the labels that we're going to use for training later on. Now we have these functions, how to get labels and how to get WAV files, and we'll bring into the mix the Scikit-learn. So Scikit-learn, you'll find here at Scikit-learn, scikit-learn.org. It's a bunch of tools to use for data analysis and machine learning in Python. So there are tools for regression, classification, clustering, dimensionality reduction, some preprocessing. So it's a very used tool in the world of machine learning and data analysis. And here we have from Scikit-learn model selection something called the Stratified ShuffleSplit. And this is a cross-validation object that is a merge of stratified k-fold and ShuffleSplit that will return stratified randomized folds, and the folds they are made by preserving the percentage of samples for each class. So this is something we want. We want to have the same percentage, the percentage of samples for each class in our training set, in our validation set, in our testing set. Of course, there are many different uses. You can use this stratified ShuffleSplit in many different ways. It's not necessary in our example, but I just wanted to bring into the mix so you know that it exists and you know that you can explore and go through tutorials specifically about this. Before we define our stratified ShuffleSplit, we will have here go through the files, and we'll have a list with the files labels. So we're going through the files, we are calling this get label file, and we have a list of labels, all the files. Then we're importing the stratified ShuffleSplit from the Scikit-learn. We're defining that we're going to use 1, the number of splits equals to 1. We want that the test size to be 20%. Why 20%? Because here in this tutorial they are using that the test is 10% and the validation is 10%. So what we're going to do, we will first run this stratified ShuffleSplit between training and test. So we will have 80% and 20%. Then from this 20%, that is the test, we will divide into a validation and a proper test. And so we will split in half, and then we will have 10% of the total files to the validation and 10% testing. So here is the first time we are using our stratified ShuffleSplit. Then we are having here our train files and our test and validation set. Then we will go through. There is a more efficient way how to do this, but I'm just showing to make it a bit more simple and you can easily understand. Now we need just the test and validation labels. So we go through the test validation set and we get the test and validation labels. And now we'll run a second stratified ShuffleSplit. And this time the test size will be 0.5 because we want to split in half. So half will be the test files and half will be the validation files. And now if we print, we will see that we have the same number. Training size, training set size is 6,400 like we had here. Validation is 800 and the test size is 800. And in theory we have now somehow the percentage of samples in each class, they are equally distributed in the subsets. So we've done here, we introduced the stratified ShuffleSplit. So you can have more than number of splits. You can define the proportion between train size and test size. We also have a random state to control the randomness of the training and testing indices produced. Here you find some example on how to use, and here more examples where we use the stratified ShuffleSplit. And here we can continue. Now we will apply what is called the process path to build the training set to extract the audio label pairs and check results. What it is doing here is using something called the Tensorflow Dataset that represents a set of elements. It defines and supports writing pipelines So we can create a source data set for your input data. We can apply transformations to preprocess the data, and we can iterate over the data set and process its elements. So one simple way to create data set is to create from a Python list. This is what we're doing here, the same what they are using in this tutorial. So we have this, for example, the training files, which we got from the previous stage, and is creating a TensorFlow dataset from tensor slices. Then there will be this waveform dataset and its mapping. So it will call this function getWaveformALabel, which is defined here, getWaveformALabel. So the label is using this getLabel from a file path, and there will be this audio binary that is using this TensorFlow IO read file, and there will be this decode audio from this audio binary. Then we have here our waveform. So tf.io read file, let's take a look. This reads and outputs the entire content of an input file name. So it's reading from this wave file, and here we see this decode audio. So now we have this information that is being read from a wave file, but we need to decode this wave. So this information now we will tell, okay, so this information what we have is a wave file, and we want to have the samples and the sampling rate for this. And here there is this function, and when we have our data set, we can use this map, and we will apply this getWaveformALabel. So let's take a look at this data set map. So it maps a map function across the elements of this data set. So it applies this to each element and returns a new data set containing the transformed elements in the same order as they appeared in the input. And this map function can be used to change both the values and the structure of dataset elements. So there are many examples here how you can use this function, and there is this thing called the number of parallel calls, represents the number of elements to process asynchronous in parallel, and if it's not specified, the elements will be processed sequentially. And if it's used auto-tune, then the number of parallel calls is set dynamically based on available CPU, and this is what's doing here. Auto-tune is set into tf.data.Auto-tune, and when it's mapping is using this number of parallel calls auto-tune, so it will assess the what is available, the CPU, and will define the number of parallel calls dynamically based on the available CPU. So let's run this, and now we will examine a few audio waveforms with their corresponding labels. So there will be a plot, and we will see here we are taking this waveform dataset now because we use this files dataset, map this files dataset to get the waveformALabel, and here we will plot. So we have here 9 different samples from this dataset. We can plot the waveform. So this is the signal, the command stop, stop, go, down, go, yes. So this way we are going through some values of this waveform dataset, and we're plotting some commands. Okay? So if you remember, in our PyTorch we did very similar thing, but we used deep learning to extract features. Then we had in this classifier, so we didn't use handcrafted features or engineered features. So we didn't use some pre-processing to get some features and then classify these features. We got the audio samples, And then we had these convolutional neural networks where we had then different representation of this audio. Now from a 1D we move to a 2D, so it's something similar to a spectrogram, but it's the features they are generating through this optimization. So this time we will first transform the audio samples into something that is already known. So it's a spectrogram, so it's a time frequency representation using the short time Fourier transform, and we are converting this audio from the time domain to the time frequency domain. So before, when we had the PyTorch example, we didn't do this approach. We used a different technique. So sometimes you can experiment and see different applications. You can use different techniques. So this is interesting that we can see now that will convert the waveform into a spectrogram. And for that, it also exists a Fourier transform function in TensorFlow that converts a signal to its component frequencies. And we also have the short time Fourier transform that it will transform our time domain into a time frequency domain. We need to produce an array of complex numbers representing magnitude and phase. But for this tutorial, we will only stay with the magnitude. And there are certain parameters when you use the short time Fourier transform. You can choose the frame length, frame step, and this is how we generate this spectrogram. They are defining here a get spectrogram function from the waveform. First, what they do is they pad for files with less than 16,000 samples. That means that we will include zeros. So if a file has less than 16,000 samples, we will fill with zeros until we reach 16,000 samples. And we concatenate this audio with the padding in order to do this zero filling. So it's called zero padding. And then we will have equal length audio files. So usually it's very common to trim and pad depending on the application and depending on your model. You will need to have files with the same length. Otherwise, it will not work. The algorithm, what you're going to use, sometimes requires to have files with the same length. Sometimes also for mini batch training and different types of training, we need to use files with the same length. And one way to do this is we can, for example, trim files that they are longer than 16,000 samples. So for example, if we use a sampling frequency of 16,000, then it's exactly 1 second. And if the files are shorter than the 16,000 samples, or 1 second, then we fill with zeros. So they all will have the same length. Of course, there are many drawbacks as well. So if you take a file that it's like 1 millisecond and you fill it with zeros, and then you have a file that is 16 seconds and you shorten it to 1 second, you're losing a lot of information. But sometimes you need to do this, and it's good to use this. And for this tutorial, they are using this. So let's run the cell. We have this get spectrogram. Now we will explore the data and we will compare the waveform and the spectrogram, the audio of one example of the dataset. So for waveform and label in a waveform dataset, take 1. Here we are getting our label. We're converting the tensor into a NumPy, also for plotting. We are getting the spectrogram. Now we are printing the waveform shape, the spectrogram shape, and we will also listen to this audio with a sampling rate of 16 kilohertz. So we have the label is stop, so we should hear stop when we play it back. The waveform shape has 16 kilohertz, so 1 second, and the spectrogram shape with the parameters that they defined here in this. So they use the frame length of 255 and a frame step of 100 28. So there are other nomenclatures also. Instead of frame length, you also see the number of FFT, the number or the window length. Instead of frame step, you also find other names such as the hop length, and sometimes hop length is also defined in percentage. So if you are interested in short time Fourier transform, you can find tutorials. We also have in our courses at the UMNL University of Technology, we explore time frequency domain representation and different types of short time Fourier transform, wavelets, and things like this. So I encourage you to go through some playlists in Guitars AI YouTube channel. Here we'll listen to stop.
Stop. Stop. Stop.
Okay, so I can understand stop, and hopefully our model, after being trained, will also understand that this is a stop. Next, they define a plot spectrogram function that converts the frequencies to log scale and transpose so the time is represented in the x-axis, and then it will axis and it will plot. Oh, it's very common to use log scales in Fourier transforms, and also it's very common to have the time in the x-axis and the magnitude or phase in the y-axis. Let's run this cell and we should get a plot. So here we have the waveform, and here we have the spectrogram. So we went from this one-dimensional time domain to a time frequency domain. So we have now two dimensions, and the dimensions are given here. So it's 124 by 129. And here we will also transform the waveform dataset to have spectrogram images and their corresponding labels as integers. So we have this waveform dataset, and once again we will map this dataset so we get the spectrogram. So we have this define function get spectrogram and label. The label is the same process what we did before, but now we are converting the labels into integers, and here we are creating the next dataset. So is this spectrogram dataset using the map function that we've seen previously. And now we will examine some spectrogram images for different samples of the dataset, similar to what we did before with the waveforms. So here we have different spectrograms for 9 different audio files. First we had our wave files. We loaded these wave files, reading the wave file, then we decoded the wave file, then we had the waveforms, then we applied short time Fourier transform, and we went from the waveforms to the spectrograms, and this is what we are going to use to classify the audio files. So as I mentioned before, it's a different approach than what we did in the previous tutorial about this topic when we used PyTorch. So we finished, let's call the pre-processing our dataset. So we prepared, we created dataset, we split into a training set, a validation set, and a test set using a stratified shuffle based on cross-validation, k-folds, and shuffle split. Then we now have a two-dimension data in terms of spectrogram, and we will now build and train the model. So before we do this, we need to get the spectrogram not only for the training dataset that we've been using so far, but also for the validation and the test set. So this is what we are doing here to pre-process the data. So we have the files dataset that takes from the files. Then we'll have the output dataset that will map, get waveform and label from the files. And then from the waveform and label, we'll get the spectrogram. So we are combining everything what we did before in this preprocess, and then we'll call. So the training dataset is already the spectrogram dataset that we used to demonstrate steps. Now we have the validation dataset, which will preprocess, and we'll use the validation files. And here we have the test and with the test files. So let's run these cells. And now we start defining actually the model for training. In this tutorial, we will use a batch size of 64. So then you can have this training dataset and validation dataset. You call this dataset.batch with the batch size. So if we go here to dataset, there will be also this function batch that combines consecutive elements of this dataset into batches. The components of the resulting element will have an additional altered dimension, which will be the batch size. So when you're working with TensorFlow and Keras, you need to take care of the sizes, dimensions of tensors, and there are some models and layers that expect a certain size and shape. Here, when we use this for batch, it already reshapes according to what we define. So let's run this, and now we will have our training dataset according to this batch size of 64. Then there will be this dataset cache and dataset prefetch operations. They are used to reduce the read latency while training the model. So let's take a look of this cache. So the cache, it caches the elements in the dataset. So the first time the dataset is iterated over, its elements will be cached either in the specified file or in memory. And this will make our reading to run faster. And another is the function prefetch. The prefetch creates a dataset that prefetches elements from this dataset. So most dataset input pipelines should end with a call to prefetch, and this allows later elements to be prepared while the current element is being processed, and it improves latency and throughput, but at the cost of using additional memory to store prefetched elements. So we are using catch and prefetch operations to reduce the read latency while training the model, and we're using also this auto tune, and we will try to use some parallel computations if there is CPU available. So we have this for training and validation. Now for the model, it will use a convolutional neural network, and it will use a resizing layer to downsample the input to make the model train faster, and a normalization layer to normalize each pixel in the image based on its mean and standard deviation. So it's a common practice when you are working with machine learning, and we always have this normalization. Mostly is to have zero mean and unit variance, for example. And here what they are doing is they are creating here now is a model using this sequential way. So there are a functional way how to create models, but also a sequential way. There will be some pre-processing, normalization. Then we see here we are resizing. We have a layer, input layer, where we give the input shape, we resize, and pre-processing, resizing 32 by 32. So this resizing layer resizes the batched image input to the target height and width, and the input should be a 4D tensor with a certain format. Then we will have our images now. It will move from the original size they have to 32 by 32. So this is a 2D convolutional layer. The layer creates a convolutional kernel that is convolved with the layer input to produce a tensor. So we will have input shape and also the kernel size, and we will use the activation function called relu. Then we will have another convolutional 2D layer. We will have max pooling and dropout. Then we will flatten. Finally, we will add a dense layer with also the relu activation. Then we will have a dropout, and then we will have a final dense layer. This is not a tutorial on convolutional neural networks. I have different tutorials when I explain this in more details, and you'll find excellent tutorials on the internet about convolutional neural networks, and it will explain in more detail what the convolution 2D is doing, what max pooling is doing, why sometimes we use a dropout, flatten, why we use also dense layers after some convolutional layers, and what are the activation functions that we use. And finally, there's this model summary that will print a summary of the model. We'll run, we'll see that there is an input shape 124 by 129 1. Now this is printing here from one example. Then we have this sequential model, and we have all the layers that we discussed before. It also gives you the total of parameters, and the total of trainable parameters, and the total number of non-trainable parameters. So after we define our model, we also compile the model, and this is where we will choose what optimizer we are going to use. So this tutorial we are going to use the ADAM optimizer. So it's a modified version of gradient descent, and you will also find a lot stochastic gradient descent being used, or other variations of gradient descent. Here also we use we define which loss we are going to use for our models. Sometimes we also can use different combinations of different losses. And in this tutorial we are going to use the sparse categorical cross entropy. That's very used for multi-class classifications. In our case, we have a certain number of labels, that are number of classes, and we will use the sparse categorical cross entropy, so we can go and compile model. And now we will train our model, and we will use this model fit. But before we do this, we will start changing a little bit, because we want to use Tensorboard to visualize this training. Now we will load the Tensorboard extension, include one more cell here. So now we will define a Tensorboard callback. So in next step on training, we'll define some callbacks, and they are using an early stopping. So if the training doesn't improve within a certain threshold, it will stop and tell, okay, it's trained enough, it's not improving. We can also have different callbacks, for example, for saving the best model in the Tensorboard callback, for example. So here now we are defining a log directory where the logs of the Tensorboard will be stored, and we're changing here using some date. We're joining logs with some date and time. Here we're defining our TensorFlow callback. So there is this TensorFlow Keras callbacks, Tensorboard. We have this frequency and the log directory. So what we need to do is we need to find this. So I should import this date time first. Forgot to import date time and OS. And now here we will have to give it a list of here, list of callbacks. And before we start training, let's start our TensorBoard. It's launching TensorBoard here. So at the moment there is nothing going on. There's no logged data. So we will define to run for 10 epochs. We will use the training dataset and we use the validation dataset for validations, and we're calling this callbacks. So let's start training. It's on epoch 1 of 10, and it takes quite a time. We have our first epoch. If we reload here, now we have our accuracy and our loss. And we can check here our model. So we have our ADAM optimizer, the sequential model, everything what we defined. See this very complex graph, have this sparse categorical cross entropy loss, and we have our, we see the accuracy is improving, the loss is decreasing. We have for the training and for the validation. So we already finished the 10 epochs, and we achieved an accuracy of 0.8375. And let's check the training and validation loss curves. So we already seen using TensorBoard, but we can also plot using the history. We have the loss and the validation loss. Here we have history, and we are training our model, so it's going to be saved here, and we can plot. And then we will evaluate the test set performance. So we will run the model on the test set, so it's already trained, and we'll see how it performs on the test set. So here we are having this test audio and test labels. For audio and label in test dataset, we're appending, so we're creating this list with audio to NumPy and label to NumPy. So we're converting tensors to NumPy. So then we'll converting then this list to arrays. So we have a test audio and test labels as arrays. So now we will predict. So we are calling model.predict. We give the test audio array that we defined here. Then we will get a prediction, and then the y true is the true labels. Then we will check the accuracy. So it's the sum where the prediction is equal to the ground truth divided by the length, and we'll see the test set accuracy. So we have the test set accuracy at 81%. It's also common to display a confusion matrix. It's helpful to see how well the model did on each of the commands in the test set. So there is this TensorFlow confusion matrix, very convenient. There's also a way how you do the confusion matrix, for example, using Scikit-learn. Here we are going to use this confusion matrix is given by TensorFlow. And we have here, for example, Go 75. So we have 100 Go commands. 75 times it was correctly classified as Go, but then we had mistakes. So it's thinking that Go is a no, also down, and 5 for yes, and 2 for up. So we see that mostly it's correctly classifying, with the right having a 92, so making very few, only 8 mistakes. So we can run inference on an audio file. So we will verify a model's prediction output using an audio file. Someone saying no, for example. So we're loading the sample file is a no command. We're preprocessing, so we're getting from the wave file, we're getting to the time frequency domain. Then it will make the predictions for no. So this is what it would do. It would, when we infer, it will generate the predictions for no, and then it would pick up the one with the maximum number. 0.6 is no or no, and then okay, this is the argmax part here. We are doing here also doing this selection of the prediction that gets a higher value. We can see that the model recognized the audio command as no. So we reached the end of our tutorial. Of course, you can also check out the PyTorch and compare. We can also listen to, we could record now that we are saying a command and see how the model classifies. It's a very simple model that achieved, for this toy example, 81% of accuracy, and you should always be very careful about these metrics. What do they mean? If you have enough big enough data set to draw conclusions from your experiment. But here you have a basics how to use TensorFlow in the Google Colab notebook. So we introduced also Scikit-learn, where you can use stratified shuffle to split the data set. And we also introduced how to use TensorBoard together with TensorFlow, and it's a complete example. You define a model, you preprocess, you train, you evaluate, and that's it for today. Until the next time.